Hello, my name is Evan Harber, and I'm a second-year master's student at Carnegie Mellon University in the Biorobotics lab. And today, I will be presenting on a tunable magnet-based tactile sensor framework. Before I begin, I just wanted to introduce the team that made this paper possible. This was a collaboration between myself, Evan Schindewolf, Victoria Webster-Wood, Howie Choset, and Luli, and is supported by MFI. In this presentation, I will be discussing a generalizable design approach to tactile sensors, a first-order model based on magnetic field and elastomer fundamentals, and an automated calibration routine which results in a fully customizable tactile sensor. To demonstrate the performance and versatility of the proposed sensor, we selected two sample design configurations, which are shown here. A small form factor that was designed for tumor localization, which we have nicknamed the pinky sensor, and a larger form factor designed for robust contact estimation on legged robots, which we call our foot sensor. These two unique cases demonstrate the breadth of sensors that can be designed using this approach, as well as how changes in sensor parameters can be used to tune the range and resolution for different applications. Tactile sensors offer a unique stream of directly measured information about physical properties. Unlike alternative approaches, which might rely on visual cues, tactile sensors offer a direct measurement of physical contact. Some previous work has been done on developing soft elastomer-based tactile sensors. Examples include the Tactile and gel site sensors, which rely on optical cues to detect elastomer deformation and have been shown to be useful in identifying objects for manipulation, as well as slip. There's also been work on the MAG1, a magnet-based tactile sensor, which has been shown to give 3 degrees of freedom force feedback. The sensor presented in this paper, shown here in a simplified form, relies on the interaction between 3 core components: the elastomer, a magnet embedded within the elastomer, and an array of Hall effect sensors used to measure the magnetic field. As forces are applied to the elastomer deforms and the magnet is displaced. By measuring the change in magnetic field, we hope to recreate the original contact forces applied to the elastomer. Using this basic framework for our elastomer design, we can tune a few parameters to achieve a desired sensing and fidelity range. For instance, by opting for a lower elastomer durometer and wall thickness, a more sensitive version of the force sensor can be created. We demonstrate this idea by constructing 2 versions of this tactile sensor. The foot sensor, which uses a high durometer rubber, thicker walls, and larger magnet in order to detect high forces under heavy impact environments, such as robot locomotion, as well as the pinky sensor, which uses a softer durometer for a highly sensitive compact environment. With mass producibility in mind, this framework is designed with durable, low-cost materials, along with scalable fabrication techniques, making the resulting sensor both easy to manufacture and significantly cheaper than traditional strain gauge sensors. Both of these sensors are fabricated by first overmolding, casting the elastomer, inserting a magnet, then rigidly fixing the setup to an array of Hall effect sensors. The model of this sensor can be broken down into 2 parts. First, the magnetic field created by the permanent magnet, which is assumed to be on the order of an inverse cubic function. And second, the position of the magnet as a function of force applied to the elastomer. The stress-strain relationship was modeled using a viscoelastic generalized Maxwell model, which introduces a time dependence into the model equation, represented here as a series of decaying exponentials. However, by taking the steady-state solution to the viscoelastic equation, you get an equation of a nonlinear spring, which has no time dependence and is far easier to fit. Combining these 2 equations, this final model can be summarized as a series of multidimensional polynomials. Calibration and validation datasets were collected using a UR3E series robot arm. The robot arm was used to manipulate the sensors and apply forces. In the case of the pinky sensor, it was trained and validated for 3 degrees of freedom, 1 normal and 2 shear forces, using an ATI Nano 25 as a ground truth. Similarly, the foot sensor was calibrated to estimate normal forces as well as contact locations using a 1D lodestar force sensor and a UR3E position force feedback as ground truth. The data sets collected during these calibration routines were used to fit our multidimensional polynomial model outlined earlier. In order to validate the real-world capabilities of our sensor, we also tested our work on 2 different robotic systems. Legged robots, with their high degree of articulation, can maneuver through unstructured environments. However, most dynamic models and controllers rely on a system that can identify the instant of foot contact as it marks a significant landmark in the gait cycle. Sensorized feet are one potential solution for the direct measurement of ground contact. By attaching the feet sensors to a basic biped robot, the sensorized feet were used to determine when to take its next step by thresholding their force measurements. By recognizing the moment when both feet are on the ground, the robot switches which leg is in the stance phase and which leg should swing. In maintaining one leg in contact with the ground, the robot is able to walk over flat as well as more uneven terrain. Similarly, for the pinky sensor, one potential application is tumor stiffness mapping. Robot-assisted minimally invasive surgery, or RMIS, augments the surgeon's limited sensory information and can be used to reduce cognitive load, allowing for better patient outcomes. Here we tested how the pinky could be used in order to measure the relative stiffness. By using a discrete palpation process that measures force versus sensor depth, we can map the relative stiffness of the tissue. Next, the boundaries are traced by thresholding the stiffness map, enabling for a better understanding of tumor size and location. This approach can clearly distinguish both tumors as well as some macroscopic tumor features, while also significantly reducing the costs needed to augment a surgeon's sensory information. Today, we presented a generalizable model and design for a highly tunable embedded magnet tactile sensor. To demonstrate its versatility, we designed and manufactured 2 different versions of the proposed sensor. A highly accurate small form factor version, which demonstrates the sensitivity and scalability of this design, and a larger foot sensor, which demonstrates the durability of the design under high impact environments, such as robotic locomotion. Both these designs utilize mass manufacturing techniques and low-cost materials, reducing the cost in comparison to traditional strain gauge sensors. These sensors demonstrate the breadth of possible designs as well as how changing parameters can be used to tune their range and resolution for a wide variety of custom applications. Our next steps for this sensor will focus on studying how parameters, such as elastomer shape, can be best picked for specific applications, allowing for a useful tool for automating tuning. We are also working on improving our model to increase the real-time response of a given sensor. We would like to acknowledge the contributions made by Steve, Nick, Mike, Shinyu, and Zixin, who also made this work possible. We have provided a QR code for a page of supplementary information, where you can locate these slides as well as some more videos of these sensors. Lastly, we would like to thank MFI for supporting this work. Thank you.